This last section is quite a doozy, so even though it's only 3 sections long, I will break this up into 2 videos. So this is video part A. The last section we're going to be talking about will include things like Lewis structures, exceptions to the octet rule, resonance, which will also include formal charge, as well as VSEPR theory. My goal is that part A video will go over these 3 sections, and the last video will be for VSEPR. So Lewis structure, you have all experienced Lewis structure in your Chem 152 days, so we'll be going through this in a little bit of a quicker fashion. In Canvas, in the extra help section, I have some really good worksheets with rules to help you remember how to do your Lewis structures. So remember that when we're doing a Lewis structure, this is for covalent compounds, and what we're doing is we're trying to depict, in a way, the bondings that occur between atoms in molecules. We know that when we form a bond, it's a sharing of 2 electrons. You can remember back to our previous video where we talked about the difference between a lone pair and a bonding pair. When we look at something like a noble gas, right, we know that hydrogen and helium will be our 2 exceptions to the rules. Instead of an octet, they're satisfied with just 2 valence shell electrons. So when we represent the Lewis structure of helium, we do so like this, and we have our lone pair of our helium atoms, and the octet is satisfied. Whereas in a hydrogen, we know that hydrogen is diatomic because it needs 2 valence shell electrons to fill that outermost shell. Therefore, 2 atoms of hydrogen come together to share those electrons. Remember that our octet rule basically is helping us get everyone to a noble gas configuration. That means 8 valence shell electrons. All of our halogens will follow kind of the same rule, and this is why all of our halogens are diatomic. We know that all of our halogens have 7 valence shell electrons, which we would draw like this for the Lewis dot diagram. We know that for this fluorine to have an octet, it needs to share 1 more electron to get an 8 valence shell electrons. So if we have 2 fluorines together, they can share their last individual electrons together to get an overall octet for both molecules. Again, if you aren't comfortable with this, when we're talking like we did in our last video, the concept of lone pairs and bonding pairs, we can see that in this model right here, we have 1 set of bonding electron pairs between these 2 fluorines, and each fluorine has 1, 2, 3 sets of lone pairs. For example, in something like neon, because neon is a noble gas, it already has its 8 valence shell electrons, right? The electronic configuration for neon would be 2s2, 2p6, which means altogether 2 and 6 gives us 8 valence shell electrons. So there's no need to do anything else to the Lewis structure of neon by itself except to draw the Lewis dot diagram. So here are some of the rules for writing Lewis structures. Again, I'm not going to go into too much detail with this because this is a review of 152. So these rules are here for you to look at. Again, as I mentioned on our Canvas extra help page, I have a very good detailed worksheet with examples where we go through quite a number of different Lewis structures, polyatomic ions, charges, things like that using these rules. So this is an example using water. We know that the first thing we need to do is identify the total number of valence shell electrons that we're going to use in our molecule. Each hydrogen produces 1 valence shell electron and the oxygen produces 6 for a total of 8 valence shell electrons. Ideally then you're going to want to identify who should be your central atom in your Lewis structure. A good rule of thumb, if you have one of one type of atom and multiples of another, the thing you have one of will be your central atom. Then you're going to start connecting these atoms together. Doing so will eat up some of the valence shell electrons. In this case we've used 4, 2 in this bond and 2 in this bond, of our 8 valence shell electrons already. Once we've done that, we still have 4 valence shell electrons that we still have to use. Usually you would go and satisfy the octets of your what we call terminal atoms, or the atoms that are on the ends. They terminate the molecule. However, in this case they're hydrogen, so their quote-unquote octets, which are only 2 electrons in the case of hydrogens, are full. So those extra electrons from our total valence shell electrons that we calculated earlier of 8, those have to go in the central atom now. So we're going to add 2 lone pairs to our oxygen. When we look at our overall molecule, we see that we have 2, 4, 6, 8. We've drawn a total of 8 valence shell electrons. From our calculation, we know that we haven't added any valence shell electrons, nor have we forgotten any. So that's a good sign. Then we go through and make sure that everyone is satisfied. Both of our hydrogens have 2 valence shell electrons that they get to claim because they are sharing with the oxygen. Our oxygen has 2, 4, 6, 8. It has a full octet. So this is satisfied as well. For the following, I would strongly encourage you to pause the video here and give this some practice. Take out a piece of notebook paper and make sure you can draw each of the following Lewis structures. Your lab this week, you also had some really good practice with Lewis structures. And at the end of this video, I will post onto our extra help page some really good resources in terms of some free online simulators for using a model kit and things like that. So I would recommend pausing here and making sure you can draw each of these Lewis structures before we go through each of them. So, HF, again, make sure you're calculating your total number of valence shell electrons. You don't want to go ahead and draw something where you've ended up magically adding extra electrons in at the end, or perhaps maybe you've forgotten some. Remember, each of these atoms is bringing so many electrons into the molecule, so those need to be represented somehow. So here is the proper Lewis structures for each of the following examples that we had. Again, please make sure when you're drawing your Lewis structures that you're adding your lone pairs. You do need to add your lone pairs. And lastly, remember that when we have a charged species, like we do here with the NO+, that you are representing that charge by putting a bracket over the Lewis structure and then giving the overall charge here. Which of the following does not contain at least one double bond in the Lewis structure? To go through and do this, again, you're going to have to draw your Lewis structures and figure that out. When we go through it, we see that C3H8 is the only one in which we're not going to have a double bond. A, B, and C all are going to have a double bond, or excuse me, A and C will have a double bond between the carbon and the oxygen, and in B we're going to have a CC double bond. Now, the following exceptions to the octet rule, this is primarily for your homework. You will see these examples pop up a lot in your homework, so I did want to talk about them. However, I won't really be having them be a spotlight of our tests and quizzes. So boron is the first of a couple of different atoms where we'll see some odd exceptions to the octet rule. Mainly the thing here is boron's happy with 6 valence shell electrons. Again, this will come down to things having to do with their electronic configuration. We're not going to go into too much detail with it. Just be aware that boron will tend to form molecules that are very happy and stable that have less than 8 valence shell electrons around the boron. Typically we'll see it forming 3 bonds. The octet rule is satisfied by drawing this double bond. However, the characteristic of boron, like we have it here right now, molecules in which the boron is electron deficient. So again, we don't really see a fluorine doing something like this, right? This double bond. This should kind of be a red flag to you that something looks odd here. Our hydrogens and our halogens, fluorine, chlorine, bromine, iodine, they all like to have just one bond. The other atom that we'll see a lot of exceptions to the octet rule with are sulfur. Sulfurs are very stable, and what will end up happening is because they have access to d orbitals, they can break the octet rule and actually have more than 8 valence shell electrons. So in this case here, we see 2, 4, 6, 8, 10, 12 valence shell electrons around this sulfur, and this is perfectly stable. As we said before, primarily the reason sulfur can exceed the octet rule has a lot to do with its electronic configuration. If you look on the periodic table, we know that sulfur is down in the n equals 3, which means it does have access to the 3d orbitals. It doesn't fill any of them up, however the 3d does exist, and because that 3d is empty, when we have these extra bondings occur, we can utilize some of that 3D as a way to accommodate these extra bonds. Another really good example of an octet rule exception would be phosphorus, and it kind of falls in the same category as sulfur. If you look on the periodic table, you should be able to explain to yourself why phosphorus behaves just like sulfur. So I would like you to go ahead and draw the Lewis structure for PCl5, using the rules for Lewis structures as we know them, but also using the understanding of the expanded octet rule. So I'll pause here and you can take a moment to draw the Lewis structure for PCl5. So as we're going through PCl5, make sure that you first calculate your total number of valence shell electrons. Each phosphorus, the phosphorus donates 5 valence shell electrons. Each of the chlorines donates 7, and we have 5 of those for a grand total of 40 electrons. We know we will have our phosphorus in the center and our chlorine surrounding it. And then obviously we need to have a bond to each of those. So when we did that, we used up 2, 4, 6, 8, 10 of our 40 electrons. So we still need to utilize 30 of our electrons somewhere else. And we know that the next rule is to then distribute the remaining electrons around the terminal atoms first. And when we do that, we satisfy up the remaining 30 electrons. This is the proper Lewis structure for PCl5. Now, sometimes we will have more than one atom exceed the octet rule. And a really good example of this would be I3-. Here we know that when we calculate the valence shell electrons, total valence shell electrons of I3-, we end up with 22 valence shell electrons. And when we go through, we end up with a Lewis structure that resembles something like this. In the central iodine will again exceed that octet rule. So here are some examples of different molecules where we're going to have violations in the octet rule. So I will encourage you to pause the video here to go through and give these a shot. Go through our rules using the Lewis structures. Using the Lewis structure rules to draw out each of these molecules. And then as we go through them, you can start playing your video again and double check your answers. ClF3, the chlorine atom is in the third row, right, and accepts the extra electrons, again because we have access to the d orbital here. And again, our rules tell us if we have one of one thing and multiple of another type of thing, typically this would be our central atom. So we have our 3 fluorines, each sharing 2 electrons with the chlorine for 2, 4, 6. Then we add our our terminal valence shell electrons to our terminal atoms. And then there are 4 valence shell electrons left over when we do this, so those will end up on the central atom in this case. Radon, we see that this is the overall structure for radon. Again, because radon, the noble gas, is in a period 6, it has access to orbitals where it can accommodate those extra electrons. In this case, for the ICl4-, we see that the iodine will be the one that will exceed the octet rule, again being further down on the periodic table. Now, for a good example, when you're drawing, I would encourage you to go draw the Lewis structure of CO3-2. Make sure that you know what that looks like. Where does the -2 come from? How do we end up with a -2 for overall on our molecule? How do we know how many valence shell electrons should be associated with that? And then you can go through and answer this question. So the best way to go about answering this question would first be to correctly draw the Lewis structure of CO3 minus 2, and then you can go through and try and identify who would be the closest related one to that. So I'll pause the video here. I encourage you to go draw these and give it a shot. The correct answer is the NO3 minus. The number of atoms and the electron count are the same for NO3 minus as they are for CO3 2 minus. Thus, these two similar ions have similar Lewis structures. As you're going through it, you may have been tempted to say the SO3 2 minus, but remember, because sulfur can break the octet rule, this will actually have a different overall structure where the NO3 minus will be much more closely related to the CO3 minus 2. Again, looking at these, this is kind of just an example of going through and which one of these molecules will violate the octet rule. Molecules or ions, because we do have some ions in here as well. And hopefully you remember that I3 minus was one of our examples where the iodine in the center will accept more than 8 valence shell electrons. The last section we're going to talk about in this video is resonance. Two things will be talked about in this video. One, what is resonance? And two, how do we pick the best Lewis structure of our resonance structures to represent the overall structure of the molecule? And we do that through formal charge. So first we're going to talk about resonance structures and what those are, and then we'll move on to formal charge. So you may have noticed as you start practicing again with your Lewis structures that oftentimes, depending on how your brain works, you might come up with a different Lewis structure than the one that is provided in the manual or in the textbook, and you may be wondering, well, why isn't mine right? Oftentimes, especially in things like some of our polyatomic ions, there may be a double bond that would be equivalent in multiple places. For example, in this NO3 minus Lewis structure that we have, we can see that the double bond kind of rotates around the molecule. These would all be considered resonance structures of each other. They're technically different. If I called this oxygen A, oxygen B, and oxygen C, the double bond went from oxygen A to oxygen B to oxygen C. So they're technically different, but they're also equivalent to each other. I could keep rotating this molecule around and keep having this double bond being in this top position. So this double-headed arrow like we see here is representing what we call resonance structure. Or it's just saying that these molecules, the way they're drawn, are all equivalent to each other. And oftentimes, the resulting structure would be the average of all of these. So if again we're kind of looking at this in terms of, well, how do we know what this would look like? Remember that a double bond is shorter than a single bond. So if we took a crystal of NO3 minus, we would see that overall, when we measured the distance between the N and the O of each of these molecules, that would be the average of each of these. So sometimes the double bond is here, sometimes the double bond is here, and sometimes the double bond is here. So all of these bonds, when we look at the average of an individual crystal structure, would show that they're slightly shorter than a single bond, but slightly longer than a double bond. So that would be the average of all of them together. Resonance structures are very important because what they'll help us do is kind of identify differences between the placement of different electrons. This is really important when we're talking about things like the electron, the LE model that we talked about earlier in the previous video. Remember again, this is where we're talking about the difference between a bonded pair and a lone pair. So let's use the NO2 minus nitrite anion as a good example of this. So we're going to describe the electronic arrangement of the nitrite anion using the localized electron model. So before we can do any of this, we have to have a proper Lewis structure for this. So we're going to go through and calculate our total number of valence shell electrons. We're going to go through and identify who would be our central atom, put our atoms around it, start connecting those atoms together, right? So if we had 18 valence shell electrons in total that we needed to use, we have 2, 4 electrons are used to go ahead and connect everyone together, which means we have 14 remaining electrons that have to be used. Our rules tell us to first go through and satisfy the octets of the surrounding atoms, and then any extra electrons go onto our central atom. So as we go through this, we end up with two possibilities for our atom, or excuse me, for our molecule. The double bond between an N and an O over here, or the double bond on the N and the O over here. We notice these are both considered resonance structures of each other. They're equivalent in terms of where the double bond is. They're just located on opposite sides. So this is very easy to see in terms of them being equivalent to each other, but this won't always be the case. So we're going to start talking about in the next section what happens when we have non-equivalent resonance structures of each other. When we have something like, before we do that, let's talk about odd number electron molecules. So if you're drawing your Lewis structures, occasionally we will run into some oddballs, just like we saw with our expanded octets, where you will run into a situation, for example, nitric oxide, where we have an odd number of valence shell electrons to work with. And I would like you to go ahead and try and draw the Lewis structure for nitric oxide and see how that odd number of electrons will work out. Again, you may feel uncomfortable drawing this Lewis structure because it doesn't look right to you. That is a good sign in terms of coming to an idea of what should be happening in a Lewis structure and what shouldn't be happening in a Lewis structure. It's just important to recognize that occasionally these exceptions and odd Lewis structures do occur. So our last topic in this video will cover formal charge. Formal charge is a way for us to determine which of the Lewis structures we've drawn is the best representation of that covalent compound. So what we do is it's a little bit of math using your Lewis structure where we determine the difference between the number of valence shell electrons on the atom if it were by itself, or we say the free atom, and the number of valence shell electrons assigned to it in the molecule in the Lewis structure that you've drawn. And this is a really good way to evaluate non-equivalent Lewis structures. So remember, up until now, when we've talked about Lewis structures, we've been talking about equivalent Lewis structures, where if you just drew this Lewis structure, that would be correct. There's no energetic differences or anything like that between these two Lewis structures. But that's not always the case. Sometimes you may draw two totally different Lewis structures and you want to figure out which one is the best fit. So information required to determine formal charge. Like we said, formal charge is kind of this way that we will determine, and we'll set some rules up for it, which is the best Lewis structure between non-equivalent Lewis structures. We need to know the number of valence shell electrons in the free neutral atom. So again, when we say a free neutral atom, what we're talking about is an atom with zero net charge because the number of electrons equals the number of protons. So for example, an oxygen, the total number of valence shell electrons in the free neutral atom of an oxygen would be 6. In a carbon, it would be 4. In a nitrogen, it would be 5. And then we also need to know the number of valence shell electrons belonging to the atom in the molecule. And again, this would be dependent upon the molecule that you've drawn. So how do we determine formal charge? First, we're going to assign the valence shell electrons in the molecule to the various atoms, making the following assumptions. Okay, so we do have a couple, again, this is based off of the Lewis structure that you're drawing. The lone pair electrons will belong entirely to the atom in question. So if we have H2O, right, hydrogen, oxygen with 2 lone pairs, and then another hydrogen, those 2 lone pairs are going to directly belong to that oxygen. Shared electrons are divided equally between the two shared atoms. So if we go back to our water molecule, we had 2 lone pairs, which was 4 electrons, and each of the shared bonds that goes to the hydrogen, one of those electrons each will go to the oxygen. So we have a little bit of an equation we use for this. The number of valence shell electrons assigned to a given atom is calculated as followed. The valence shell electrons assigned will be the number of lone pair electrons plus 1/2 the number of shared electrons. Or you could say number of lone pair electrons plus 1/2 of the bonded electrons, right? So this would be lone pair electrons versus bonded pair electrons. Atoms in a molecule try to achieve formal charges that are closer to zero. The closer we can get a formal charge to zero for our overall molecule, the more likely that is the best Lewis structure. Any negative formal charges are expected to reside on the most electronegative atoms. So if you have a Lewis structure, and you have two non-equivalent Lewis structures, if you can, when you calculate the formal charges, if you can put the negative formal charge on the oxygen or the nitrogen, you're going to want to have the Lewis structure where the negative charge is on the more electronegative atom. So we have rules that will help us guide us through our formal charges. To calculate formal charge on an atom, take the sum of the lone pair of electrons and 1/2 of the shared electrons. So this is the lone pair electrons. How many lone pair electrons are there? Plus 1/2 of the bonded electrons, or the electrons that are shared with other atoms. This is the number of valence shell electrons assigned to the atom in the molecule that you drew. Remember, this is trying to validate a Lewis structure that you are drawing. We're going to subtract that number that you did here, that assigned number, from the number of valence shell electrons on the free neutral atom. That will give us a formal charge. The sum of the formal charges on all the atoms in the molecule you drew, or in the ion, we could do it with ions as well, must be equal to the overall charge of that species. Non-equivalent Lewis structures. When we go through, we're going to compare these non-equivalent Lewis structures by looking at the formal charges. If we can find a formal charge where, a Lewis structure where we have all 0 formal charges in one of them, and one where we have some actual charges to our formal charge, the one with all zeros would be the more desirable one. And the one, if we have negative charges, where the negative charge is on the most electronegative atom, would also be the more desirable Lewis structure. So we're going to go through and we're going to do this with xenon trioxide, which is a very explosive compound. Which Lewis structure on the structures are the most appropriate according to formal charge? Now, I will pause here. I would encourage you to pause and try drawing a couple of different Lewis structures for this before you move on. However, be aware that there are quite a few Lewis structures, so you may not be able to think of them all. This is just a really good example for us to look at the different formal charges. So there actually are 8 different Lewis structures that are possible to draw out for a xenon trioxide. And here they are. So as we can see, we can have xenon and 3 oxygens all singly bound. We could have a double bond that we would rotate through. And remember, these are all equivalent Lewis structures to each other. We could have 2 double bonds that could be rotated through as well. So when you go through, we can calculate the formal charge on each of these atoms. I would strongly encourage you to pause the video here and go through and calculate the formal charge on each of these atoms and double check to see if you get the same formal charges. Again, this is going through counting how many shared electrons there are versus and how many lone pairs there are. So we add up the number of lone pairs. So here there are 6 lone pair electrons, right? And we have the shared electrons here. So we have 1, 2, 3 sets of lone pairs, and we have our electrons in here, which we take half of. And we compare that to the 6 valence shell electrons that the free oxygen would have. That's how we end up with a -1. So go through and do that for each of these for each of these atoms and see if you get the same formal charges. Hopefully you're recognizing that one of our structures, this one down here, we see that there's a 0 formal charge for each atom. All these other cases, we have some formal charges associated with them. Even though overall we see that they cancel out, right? A +1 and a -1 gives us an overall neutral atom. A +1 and a -1 gives us an overall neutral atom. A -1, a -1, and a -1, and a +3 gives us an overall neutral atom. So they're all correct structures technically, and they're different from each other. So we have to determine which one is the best Lewis structure, and we do that looking at their formal charges. And in this case, the one where we have all zeros for the formal charge will be the most stable Lewis structure. So this is our best option. Again, you may be given a question on a test or a quiz where you're given this information. You might not even need to draw it all out or figure it all out, but you may need to explain why one choice is the best. So make sure that you are comfortable with that concept. So when you're doing formal charge, it provides an estimate of the charge. It should not be considered an actual atomic charge. Again, remember these are Lewis structures of covalent compounds. So they're not real charges. We're not talking about ionic compounds here. This is just a way for us to kind of understand the stability that we're seeing in our Lewis structures. So how many resonance structures does the molecule SO2 have? So this would again be some very good practice with drawing Lewis structures, coming up with different Lewis structures that we could have for SO2. So I would encourage you to pause the video here and start drawing out different Lewis structures for SO2. There are two different Lewis structures for SO2 without lone pairs, where we have an S double bound, or excuse me, a sulfur double bound to an oxygen in a single bond, or on the opposite side, the double bond and a single bond. Which of the following statements is correct considering Lewis structures? The concept of resonance can be used because the Lewis structure model is incomplete when describing bonding in a molecule, right? Lewis structures show static, localized electrons. Remember, this is like a snapshot, like a picture. Remember, electrons are always moving, and that the Lewis structures that we're drawing are a model for understanding these stabilities, right? These structures are incomplete because electrons are better thought of as delocalized in the molecule. Or basically, you can think of electrons kind of like electrons flowing in a circuit when they're flowing in a molecule. Those bonds are kind of like the wires that allow those electrons to flow through them. So they're delocalized, right? So sometimes double bonds will move. That's why we said earlier when we were looking at the NO2 structures, where we said, well, it's the average of all three of these resonance structures together because of the delocalization of the electrons as they flow through. This will be the end of our Part A video for our last section of Chapter 8. In our next video, we will talk about Vesper theory.